This video will be discussing how to use Lewis dot structures to understand the bonding in molecules and compounds. Lewis dot structures are a convenient way to represent the valence electrons in a particular atom and therefore give us some information about how we can go about connecting atoms to one another to form molecules. So what we can do to write a Lewis dot structure for a particular atom is we focus in on the number of electrons that are in the valence shell, which can be obtained from the shorthand or the abbreviated form of the Lewis dot structure. And we represent those electrons as dots that are going to surround the atomic symbol. We generally have 4 different regions that we have around the atomic symbol. In this case, we have a chlorine atom. We have dots that are at the top and the bottom, as well as the left and the right of the atomic symbol. In this case, for a chlorine atom, there are 7 electrons in the valence shell, and so you see here 7 dots surrounding the atomic symbol. You'll notice that there are dots that form pairs of electrons, and then there's also an electron that is not paired. This corresponds very well with the orbital diagrams that we would write for the chlorine atom. So there's the unpaired electron representing the single dot to the right of the atomic symbol. This is referred to as the Lewis dot structure for the atom chlorine. Shown here are the Lewis dot structures for the elements lithium through neon, the second period elements. So in the case of lithium, there's only 1 valence electron, so hence the Lewis dot structure has only a single dot associated with it. The beryllium atom would have 2 valence electrons. We put the 2 electrons on opposite sides of the atom. Generally, we are not going to spin pair until all 4 regions around the atomic symbol have at least 1 dot in them. For boron, we have 3 valence electrons, so hence the 3 dots. And then finally we get to carbon, and there are 4 valence electrons and 4 dots. Once we get to nitrogen, we now have to begin to pair up the dots, and so in this case nitrogen has 1 pair and then 3 individual dots associated with the potential to form bonds. And then for oxygen there are 2 pairs and 2 single dots. For fluorine, there are 3 pairs and 1 single dot. And then finally, with neon, we have a closed shell with the 8 valence electrons forming 4 pairs of dots. This is a very stable electron configuration. Of course, this is a Lewis dot structure that will also be something that you will see quite often. As I indicated previously, it turns out that metals tend to lose electrons to form positively charged ions, while nonmetals tend to gain electrons to form negatively charged ions. What we have here is the reaction between sodium metal and elemental chlorine, in which an electron will be transferred from sodium to the chlorine atom. In the picture, we have a graduated cylinder that is filled with chlorine gas, slightly yellow colored gas, and in the small container to the right of that is some elemental sodium, which happens to be a solid at room temperature. If you take the sodium and place it into the chlorine, a reaction will occur that releases quite a lot of heat. The heat that is produced produces a flame, and the product, which is the ionic compound sodium chloride, is produced initially as a white smoke, which then settles to the bottom of the container. This is a fairly dramatic kind of chemical reaction that should not be done at home. The reaction itself is referred to as being exothermic because the energy that is stored in the chemical bonds of the reactants is released and goes into the surroundings in the form of both light and heat. The delta H of this reaction, the release of the heat, is a fairly large value of a negative 410, 411 kilojoules for every mole of sodium chloride that is formed. To represent this chemical reaction between sodium and chlorine, we can use the Lewis dot approach and understand what is going on in terms of the valence electrons. Shown here are the Lewis dot structures for sodium and elemental chlorine. It turns out that the sodium atom has one valence electron, whereas an isolated chlorine atom has 7 valence electrons. To become a noble gas configuration, sodium will give up its 1 electron, and it will be transferred to the chlorine atom, which has 7, but nonmetals tend to gain electrons, so chlorine would like to have a total of 8 valence electrons. This results in the formation of a sodium cation. When we write the Lewis dot structure for a cation, we write the atomic symbol. Any valence electrons are represented by dots. In the case of sodium, there are no more valence electrons. But to represent the charge, we place the atomic symbol in a bracket and then include the positive charge. For the chlorine atom, there are now 8 valence electrons, so we have 8 dots surrounding the atomic symbol for chlorine. Again, we place that inside of a bracket, and then we include the charge as the superscript to the right of that symbol. So ultimately then, the sodium atom ends up losing its dot, its valence electron, to form the sodium cation, whereas the chlorine atom gains an electron from the sodium and forms the chloride anion. In this example, the atoms that we had as reactants were relatively unstable because they didn't have closed shells of electrons, but the products indeed had noble gas electron configurations. The crucial thing is that both the cation, the sodium cation, and the anion, the chloride anion, ended up having 8 valence electrons. This is the so-called octet rule. The term octet is referring to the 8 valence electrons. There are quite a number of exceptions to this rule, however, but one thing that you can count on is that for elements in the second period, they will never violate the octet rule, at least not in terms of this class. To further demonstrate the effect of the various charges of the subatomic particles, we have a diagram here showing the number of protons in the nucleus and the number of electrons surrounding the nucleus for both the sodium atom and the chlorine atom. In the case of the starting materials, the sodium has 11 positive charges from the protons in the nucleus and 11 electrons, so hence it is neutral. But it loses 1 electron to form an ion which has 11 protons, 11 positive charges in the nucleus, but only 10 electrons. So the net charge is the sum of the 11 positives and 10 negatives, so hence the net charge of the sodium ion is +1. In the case of the chlorine atom, we start out with 17 positive charges in the nucleus from the protons and 17 electrons, so 17 negative charges, giving a net charge of 0. But by gaining 1 electron, we have 1 more negative charge than the positive charges in the nucleus, so hence chloride ions has a -1 charge. In addition to the formation of these ions in the gas phase, then, we now also have to consider the fact that we have the electrostatic attraction that occurs between those oppositely charged ions, and that then causes them to come together to form an ion pair. And of course, as more and more of these ion pairs are attracted to one another, they come together to ultimately form a crystal lattice of some sort, where there is then many sodium ions and chloride ions grouped together that then form the solid sodium chloride product. In this slide, we want to emphasize the transfer of the electrons and the formation of the ionic solid, which then releases this dramatic amount of energy, and so we wish to describe the so-called lattice energy. Initially, the electron is transferred from sodium to the chlorine atom, forming the isolated ions in the gas phase, the sodium cation and the chloride anion in the gas phase. This then results in the attractive force between the sodium positively charged sodium ion and negatively charged anion, which then forms the so-called ion pair in the gas phase. This is the formation of a bond which is between these two ions, and this is much more stable than the isolated sodium ion and chloride ion, which is not attached to one another. So this is a contributor to the release of some of the energy that is observed. In addition to that, we then have to consider what then subsequently happens to form the large groupings of atoms that are ultimately the ionic solid. Shown here is the energy that is released when the isolated sodium ions and chloride ions come together to form the ion pair in the gas phase. This is approximately a release of about 500 kilojoules per mole. In addition to that, then, is the formation of the combination of many of these ion pairs that come together to form the crystal lattice, the three-dimensional repeating pattern of sodium ions and chloride ions. This releases an additional nearly 300 kilojoules per mole of sodium chloride. So the so-called lattice energy is the sum of those two energy releases, and so we refer to that total amount of energy that is released as the so-called lattice energy. So by definition, lattice energy is the amount of energy necessary to take an ionic solid and get it to become the isolated ions in the gas phase. And so to do that, it would take putting energy into the ionic solid, as you see here, and you'll notice that the delta H is positive in this case, whereas when the ions are coming together, that is releasing energy, and so hence the negative value.